Swayam Prabha. Digital India. Educated India.
Okay, if I look at the theoretical stuff that's been done and take out the essence of this, these are some of the summaries. First of all, evolutionary algorithm, including genetic algorithms, are stochastic algorithms, as you have seen. There are multiple populations, lot of schema getting processed. They are iterative, not easy to do perfect math, okay, like in the case of a point-based method, particularly because of the stochastic nature of this algorithm and also the population part of it. But then people have tried different techniques they have used. There are three different approaches. First one is functional decomposition, which I have been a part, and I'm still doing whenever there are some basic level research we work on. It's called functional decomposition. We look into one aspect at a time. So when you are understanding what TS, what tournament size is good, we don't consider crossover and mutation. We just look into the purpose of selection. It's to get multiple copies of the best solution. How shall we do it? What value should be good? So we work on that. Or then when you are looking about the recombination, we just look at recombination, not selection and crossover. There are some papers we worked on those things. And this is more of an engineering approach because that gives us a very good way to look at one thing at a time. Both my supervisor, Dave Goldberg, and I got motivated when we were attending. I mean, many of you are from aerospace. There is a professor at University of Illinois called Gary Bradshaw. He was giving a talk about Wright brothers' approach to flight. Okay, it was a very inspiring talk. I still remember his face and the diagrams he showed. Before Wright brothers, a lot of people tried to come up with the shape of the what is known as these days aerofoil, right, or airfoil, but they were not getting at it because they were not doing a functional decomposition. They are trying this. If that failed, they will modify intuitively to something else. There was no scientific approach. Wright brothers were the first. They looked at functionally. What do we have to do? There are two things, as we know now, but that time it was poorly understood. Drag and lift. You have to have minimal drag for any shape that will be the final shape of the wing. You have to minimize drag. So you need to figure out which shape is going to minimize drag and then which shape is going to maximize lift. So they functionally decompose this flight problem into these two things, two tasks. Then they looked at, they had a wind tunnel, they looked at what shape is going to produce minimum drag and then what will maximize lift. They found there is this aerofoil shape that does both. Okay, and that was the eureka moment for them. And they built, and obviously it worked. So, and he really nicely showed with a lot of data and things like that. We got inspired and we said, we need to, but at that time, I'm talking about late 80s, almost early 90s, I think 1990 or 91, when we were attending this. We thought we need to understand this complex dynamics that genetic algorithm has when you go from one iteration to the other functionally. And that's where this functional decomposition idea came in. After that, we did one after other papers, just looking at every functionality at a time. People do not have access to some of those anymore, although there are a couple of books and all that, but we need to get into the students and young people with these kinds of a concept, this kind of engineering concept. And we had lots of resistances from the computer science people who are predominantly in this field. They don't understand this engineering approach. There's not degrading what computer scientists do, because I also do a lot of computer science stuff, but there is a basic difference in understanding of an engineering point of view versus a scientific or for a purely computing point of view. We should get into, so I think you should take this as a lesson to anything you do in life. In your research later, anything you find complex, not easy to write an equation, a PDE, and solve it and get the answer. Many things in real life cannot be solved with closed form solutions to a PDE, right? We all know that. Ask any professor, they will tell you it's not possible. So what do you do in that case? this approach is one you should think of. That there are a lot of things going on, particularly MDO kind of stuff, multidisciplinary stuff. One thing needs to be looked at from many different angles. If you try to put everything together, it's confusing. Can we decompose them functionally? Say, okay, let's look at the same problem from this functionality point of view. What kind of approach I need to use? And then is it also good for another? So you need to finally link all these approaches and disciplines together. But first, starting with the functional decomposition to a complex problem is probably one of the ways to go. All right, so that was, all these are dying now because people are not doing much of theory. So much computer power we have these days. People say, oh, we could actually do a bulwark and get all the theory you need coming out from computations. And a lot of people are doing very smart computing in order to come up with these kinds of ideas. But when I did my thesis, computers were not that powerful, so we had to take help of different analytical approaches. There are a lot of physics people who came into in the field, but kind of they have left, is this dynamics, this statistical dynamics approach. They look at this as a Markov chain. Because if you see one generation to the next, you don't need the previous 2 generations ago, what the population was, to create the current population. You only need the previous one. So it's a perfect Markov chain. So they go into math, that branch of math, and they look at it from that point of view as if this whole thing is a dynamical system. Unfortunately for these, you need a precise fitness function. Otherwise, you cannot do this. So they could do for very simple fitness functions like a square function, linear functions. So they look at the whole population statistics. For example, I have a population, I have the function value, right? How is the average going to grow with iterations? So you need to supply the fitness function and then a population size, maybe starting with random population, and they compute the average fitness of the random population, and then they simulate this application of selection crossover mutation and see how the average is going to grow. Okay? Then they look at the standard deviation, average, standard deviation, kurtosis, all of these statistical stuff they do, they see the distributions. So they predict how the distributions of the population is going to be. But the limitations came because you need to provide a function, and they were trying to do exact formulas for these, and that was not possible if the function was too difficult. Then this I got mixed up here. The dynamical systems approach is Markov chain, but this is more like the statistics, okay? So everything here, mu as a function of iteration, starting here, if I'm maximizing, how is this growing? Can I predict that? Standard deviation was very high starting, and then it's reducing with iteration, how it's doing that. Now this one is going to be bell-shaped, but if your population has this kind of a nature, one side heavy, then you have to also bring in the kurtosis. Okay, so all these, they could do first order, second order, third order moments and everything on statistics. But these guys were doing the math with the Markov chain. There is a book called Simple Genetic Algorithm. Nothing is simple about it in the book, but they named it Simple Genetic Algorithm because he's a math professor. To him, this was very simple. There are a lot of fractals and all that was there in the book. You can see nice pictures showing under what conditions GA gets attracted to the global minima. There's very nice work that's been done. So if you are a little math oriented, the name of the author is Michael Bose. You can look for it. I'm not sure if you have a copy in the library here, but it's maybe better to get a copy. Okay, so I think some of these have died. This one is still going on by some people who are Bose's students and some other his collaborators. This is also still going on in a very limited way. Okay. Now, with all of these, we have this asymptotic proof that I mentioned yesterday. But as I said, for all practical purposes, it's not useful. But I think theory is good for theory's sake. But with 40 years of work, major work in many different fields, I showed you a couple of real-world examples yesterday. I think the breadth of ES application in many different problems, complex problems, is what gives us confidence. And a lot of people are still in the field, still doing, and still it's exponentially increasing. Okay, it's this applications, but not many people are doing it in a nice way, following some of the theoretical understanding that we have. The results coming out from these analysis is the population size has to be in proportion to the number of variables. So if you take a problem with 10 variables and you thought, okay, 20 population size is enough for 10 variables, if you increase it to 20 variable, you should increase this to 40. So proportionate to the number of variables. Now 10 variable, another problem may require 40. As I said, it depends on the complexity of the function. In that case, that problem, if you increase to 20 variable, you have to increase it to 80. That, if you start with a initial random population. But I will soon show you an example where, as I said, I took a problem to all the way to 1 billion variable, 1 giga number of variables. So I don't have a giga population size. I only have 60. How is it possible? I am not starting from a random initial population. So if you have some biased initial population where you have some customization, you know something about good region of the search space, then you don't need these proportionate thing. But this is assuming you don't know anything about where potential good solutions are. In general, these are good strategies. Crossover probability from 0.8 to 1, mutation 1 over the number of variables or number of string length. If you're doing binary string, then it's 1 over the L. Loss of variance that comes because of the selection, because selection, you are picking good ones and deleting the bad ones. So obviously you are losing variance. So that variance must be replenished by crossover and mutation approach. That's the exploration issue. So when you design the PC, PM, and TS, this is what you have to keep in mind. Yeah, that's the one I was talking to you about. Mutation operator should be such that if you mutate any solution in your search space, potentially you can go to any other place in the search space with a non-zero probability. Maybe the probabilities of mutating, if this is my search space, probability of mutating this to get a point here may be very, very small, but should be non-zero. But probability of getting this as a child, very close to the parent, should be high. So you can think of a Gaussian kind of long tail mutation operator to have that. So that's very essential, that mutation should essentially take you any part in the search space. Then what's the need for crossover? Crossover is useful to combine things from 2 or more strings into 1. So that can give you very powerful recombination of ideas from different solutions. I will show you an example. The dynamical systems approach has given us this. When you do that Markov chain analysis, they do the infinite population model. So assuming there are infinite population, you could go to a fixed point. So any dynamical system who have taken a course in that, you know that there are fixed points where dynamical systems will get attracted. There may be multiple fixed points. But when you do finite population, you are making an approximation to the infinite population, and that creates lots of artificial fixed points. So when you run GA, it can get stuck into one of those artificial fixed points. And that's why if you run GA several times, you may see that your population is getting stuck at various different fixed points. But we have quite a bit of understanding from all these different kinds of theories. That's all I'm going to say, okay, about theory. Now let's move on and see constraint handling. How do we handle constraints in a GA or any evolutionary method? It's a population-based approach. Okay, usual way is this penalty function. Right? I showed you before in the context of point-based methods. You have a function that you want to minimize. You have some constraints that you want to satisfy. You can apply this bracket operator. What the bracket operator means is this is equal to alpha if alpha is greater than 0, equal to 0 otherwise. What does it mean? That means if my constraint says gx should be less than equal to 0. That's my constraint. If any x satisfies this, it's feasible. Okay. So which means this value, if it's negative, you are fine, or 0, you are fine. So if this is positive, that means if alpha is positive, then you should add a penalty equivalent to the value of g. So that's what this is. You can take the square or you need not take the square. It doesn't matter. Okay. Now I put a hat on top of G to say that you need to normalize. So that means let's take one of these constraints. Let's say 2x1 minus x2 is greater than equal to 5. Okay. So first thing I'm going to do is convert into less than. So 2x1 minus plus x2 is less than, I'm going to put it on this side. I don't know how to erase this. So then it's going to be plus 5 is less than equal to 0, right? The same constraint I did, this is less than equal to 1. Now with this right hand side, I'm going to divide. And this is what I'm going to call G1 hat. So this is my G1 hat. I normalize it with the right hand side. Why? Because I may have a stress constraint that says stress should be less than equal to strength. And the strength values are usually large, like 200 megapascal or so times 10 to the power 6 Pascal for steel, right? I can have another constant like the deflection, and that could be less than equal to, let's say, 10 millimeter. Okay? Now here, even if you have a violation, so this is S, even if you have a violation, it can be of the order of 10 to the 6. Even if it is 200, and so let's say this is 201 megapascal, so you violate by 1 megapascal. Okay? Because it's supposed to be 200, but your design says it's 201. So you violated the constraint by 1 million Pascal. On the other hand, this one, if you violate, maybe it's 10.5, and that's a violation by only 0.5. So there is a mismatch. Here it's a million, here it's only 0.5. If you just use these ones here as G, this is going to be ignored because it's such a small number compared to the other, this is going to be ignored. So what you do is you divide this by S. So you bring it on this side and less than equal to 0 and divide this by S, and you bring it on this side and divide this by 10. So now these numbers are normalized. Okay, they have more or less the same value. That's the normalization you have to do. Otherwise, it will not work properly. Okay. So with that, you add all of them, and then we saw that we talked about that penalty function can distort the landscape. I take an example. This is a welded beam design problem. I don't have the sketch here. It's like a beam. It's a well-celebrated problem in optimization literature. This has to be welded here, okay, and you apply a load at this end. So this is the cost of fabricating this. These are 4 parameters, H, L, T, B. These are related to the dimensions, weld thickness and all that. Here is the stress constraint for shear stress. Here is the normal stress. Here is some kind of geometry relationship. Here is the buckling of this end. Okay, and here is the deflection of this end. So all is restricted so that when you solve this problem, you have a x vector which is HLTV that's acceptable. So I normalize each of them. So that means I divide this by, so these are greater than, I have to convert it to less than, and then divide by 13,600, this one by 30,000, this one, how do you do? This one there is no constant. So usually we look at the lower bound, upper bound of B, lower bound, upper bound of H, and find the maximum value that can be possible from it. It's kind of a rough idea. This one by 6,000, this one by 0.25. We normalize, we add the violation and add as a penalty, and I'm now having a single objective function without any constraint. Everything is factored in here. So it's an unconstrained problem. I could use the GA that I've talked about so far, and I ran it 50 times. With that, I think this was coded in binary strings, because this I did way back, I think this was my first paper actually. So we did it in I have to be careful, 88 is when I did. This was my class project to the GA class that I took. And there was an opportunity for a conference as a student paper, I submitted this one. So it's a first application of GA to this kind of structural engineering problem. And that time we didn't have this sophisticated constraint handling method. So we were using penalty method. I ran 50 times. What happens is, when I take a penalty parameter of 10 to the 0, which is 1, out of 50 runs, 13 of them produced infeasible value because I have not given enough importance to constraint satisfaction. So constraints were easily violated. I make a complete GA run, 13 of them gives me infeasible, which is not good, right? But then 50% of my runs, which are not infeasible, 12 of those runs gave me a function value. So I know by heart this. The optimum of this is 2.381. That's the function value. We've tried it so many times. This is known optima. Okay, now it is proven to be the optima. So 1.5 times of that, I'm saying if I can get a solution 50% more than this, I'm happy. 12 of them I could find out of 37 feasible runs, which was not a big, good result, right? And you can see those 12 runs have got the best 2.41, which is 50% within 2.381. But look at the worst one. Look at the median run. So it's not something that I'm proud of, that I can give it to someone to run. Okay, then I increased to 10 my penalty parameter because this depends really on the penalty parameter. Okay, again, now because I gave more importance to constraint satisfaction, I don't get any infeasible. Every time I run, I get a feasible solution. Also 12 of them are within that, but look at now. Now I'm going away, but I've got a tighter bound because I'm not dealing with the non-satisfaction of the constraints. If I increase further, okay, I don't get any more infeasible. So from here on, I'm giving more importance to constraint satisfaction by increasing this R. So that's not a problem, but I'm going away from the minima because I'm now giving more importance to constraint satisfaction, less importance to minimizing F. Because all in one equation. Either if you put more R, you are giving more importance here. So you'll not get any infeasible solution, but you're not giving importance to minimizing F. If you give less R, you are giving importance to F, but not importance to constraint satisfaction. That's the problem when you combine things. And we'll talk about this when we get to multi-objective, okay? Because many people try to combine multiple objectives into one, and they have these issues, okay? All right, so that's the situation. I could do more fine-tuning here and maybe find a better compromise, but it's time-consuming and all that, right? So all these, during my student time and even after I came back, joined IIT Kanpur, I was interested in working with industries, and I got few industry problems and I had the same issue, fiddling with R. Then I said, I need to take care of these, okay? So then I came up with this idea. I don't know why this type equation coming here, but anyway. We came up with this concept which is now by default used, and we did this in 2000, published this in 2000. Okay, so what is it? So it only works with population-based approaches. If you don't have population, this idea doesn't work. So we are taking basically advantage that we are dealing with the population and ignore that R, because R was the culprit, right? I have to combine the two things. So how do we do? Let's say I'm doing a problem where this is my fx, as you see the dashed line. Where is the minima? It's here. But I come and say this is my feasibility bound, so this part is feasible, this part is not. So this cannot be the optima anymore. As we have taken a problem before, this becomes now my optima with this function value, right? Okay, so let's say I'm solving this problem and I have my search space going from here to there, and I create randomly 6 points, and let's say they are happening here, these 6 points. 3 of them are feasible, 3 of them are infeasible. Okay? How do I assign a fitness? Every point has a f, which is this value to the dashed line, and also a constraint violation, this gjx sum. I call this CV, constraint violation. So this is the constraint violation. Let's call this CV. So for every point, I have a F, I have a CV. CV, if it's positive, that means it's infeasible. It's not satisfying at least one of the constraints. If it's 0, the way we have defined it, it is feasible. Okay? And F can be anything, positive, negative, but my goal is to minimize. All right. So now what I look at, I have evaluated each of them for F and CV. All those points that have 0 CV, those are feasible. So that I call is class 1. Others are class 2, infeasible. Then what I do, I compute f for each of them, and I look at the one having the worst f, highest f. It is this value. Highest f for all feasible solutions, not considering infeasible. Make sense? Okay. Now I come, okay, no, before I go. So I've got that. So fitness, this is the fitness, assigned to each of the feasible solution equal to just the objective function, because constraint violation is 0, so I don't have to add anything, subtract anything. This is the function value, fitness value. So f, capital F, is equal to the objective function for all feasible solutions. Now I go to the infeasible solution set. Okay, for each of them I also have an f, I also have an CV. Okay, now let me give you an example. Let's say you are a designer of anything you are designing. Let's say this pen or the glasses I'm designing. There are a lot of parameters. I come to you and say, here is a design, I give you some numbers. Okay, what's the first thing you're going to do? So you have a lot of constraints that this has to be not very wide, so it will not fit in. This has to be doesn't have to be too narrow, so it doesn't go in. And then a lot of other things, this distance and all of that. What's the first? And then comes the cost. You are minimizing the cost, let's say. That's your objective function. But there are a lot of constraints that says, can I use it? So what will be your first thing when you get a design, when you get a solution either from a computer or somebody gives you or you come up with one? What's the first thing you're going to do? Intuitively. Yes. Check whether it's feasible. Whether can I use it? If you cannot use it, and I tell you, hey, you missed something, this is going to cost you just 1 rupee. Are you interested? Although it's 1 rupee cost? You say, no, because I cannot use it. That 1 rupee will be a waste. Nobody is going to buy my product. Right? So first thing is satisfaction of the constraints. Can I use it? Can I fabricate it? Is it going to be feasible when I fabricate it? So which means, is my CV 0 or not? If my CV is not 0, I'm not interested in F. So before me, there are a lot of people try to combine F and CV before this work. They always add F with CV. And I never understood why. Because if you are not going to be able to use it, what's the point looking at the F? And that kind of complicates things, right? So we said, no, if your solution is infeasible, that means you come here, at least one of your constraints gets violated, then I'm not interested in F. I look at how much constraint is violated. For example, for this constraint, it's infeasible. It's not over here. But I look at how much constraint is violated, which means what is this gap? For this one, what is this gap? And for that one, what is that gap? So as you go this way, you are getting more and more away from being feasible. You are more and more bad in terms of constraint satisfaction. So this one is little better than me than that, being the fact that it's close to the boundary. This one is even worse, right, than any of the other two. So that means my CV value that you compute determines how good you are being infeasible. Okay, so that's that part. What is this I'm adding here? That's this F max. Why I am adding that? Let's talk about it now. I still want to have one fitness function for all. Okay, so these ones are very clear. I look at the worst one, and okay, so if this is the one and I'm not putting a square, you see, now you have a 45-degree line here because this is same as that, and that is same as this, and this is same as that. So that means if I got a 45-degree line here, I achieve that. So these are my this part, okay? And now I'm moving this line up by this F max distance. So this is F max. So I moved that dashed line, which is the constraint violation line, by adding F max to it. So my fitness function for infeasible solution is this line from Fx, capital Fx, and this one for feasible. There is a discontinuity here, but GA is not using gradient. Doesn't matter. So what that does any infeasible solution has a worse fitness than any feasible solution. You see, that's why I'm moving it by F max. Okay, so if I compare this with that, which is better? This one is very high, large, and this one is small, so this is better. If I'm comparing any two in the feasible region here, which is better? Whichever has smaller f, because I have to go over there. And if I compare any two here in the infeasible side, which is better? The one that has small constraint violation. All of this I'm able to achieve with this f. Okay, so if you don't have any feasible solution to start with, all your solutions are here. Okay, that means all are falling here. You have a gradient that you should go in that direction for selection. A selection operator is going to choose these solutions more than that. So you have a pressure towards this direction. If you have few feasible solutions here, you have a pressure towards getting that direction. So you see, you have pressure from both sides to come near the minimum. Without, do you see any parameter here? Any parameter like R or anything you have here? Some students say, yes sir, there is one, F max. Is that a parameter? It's not a parameter, because that depends on your feasible solutions and what's the function value of the worst one. It's not a parameter, it's not something you are setting. Okay, then the question is, what if I don't have any feasible solution? What is my F max? Just put it 0. So you don't have to move it up, it's just that, because all you have is here, you don't have to move it up. Is the process clear? Very simple idea, no parameter, and it works like a charm. Okay, so once I tell you this, it makes sense. You say, yeah, but why didn't people think about it before? The reason is they haven't understood this part, that when I'm infeasible, I don't have to look into the objective function, because if you do, you are complicating things, and then sometimes it works, sometimes it doesn't work, because there is a dip here. If you're adding this with that, there will be a dip in this function. You have multiple attractors, all these complications. Just the idea that what if a practical thing is, if you have infeasible solutions, I don't care to know the cost or any of the objectives, right? So here is a simulation of how it works. Again, I don't know if you can see it, but this line here is the constraint, and initially there are points all over, but they go to the feasible region and they kind of creep towards this, because the optima is somewhere there, optima is somewhere here. Okay, and it works with this idea very nicely. The same problem I showed you with the welded beam design. No, sorry, this is another one. Can you see two lines, two kind of crescent shape feasible region I have? So in between these two lines here, there are two circles. That's the feasible region. So I handcrafted this problem to make it very, very difficult, that all these white space is infeasible except the region between these two circles. So it's a very tiny feasible space. When I start with 40 points like these circles, none of them is inside. So that's why you see start with 0. This is the number of feasible solutions. With iterations, you see, in about 10 iterations, I've got about 40% of them gone inside. In about 20, or what is it? Yeah, 20, I have about 90% of them are inside. So pretty fast, all these points moved in. And right about here, 15, 16, I've got the optima. The optimum is right there. Okay, so you see, even for such difficult problems, this idea of that they should come towards the feasible region from both sides of infeasibility, and also once you are inside, you are automatically pushed towards near the optima. So the same welded beam, remember we had so much trouble setting with R. Every time we get this, you see, this is 50 runs, 2.381 I told you. This is the best one we got. 50 run median 2.382, the worst 2.383. So it's not 470 or something. Every time you run, you get very close to what is known to be the optima. Okay. All right, so now you know how GAs work, a little bit, the GA operators, how to handle constraints, a little bit of understanding of how GAs work. So this slide onwards I have added lately, like few years now, because giving a talk like this or even 1 hour talk, there will be some people, smart people sitting and asking me questions. How big a problem have you tried? Because all along they're sitting with this recombination, selection, they think it's like a child's play. It's like some game I'm playing, it's not serious stuff. a lot of randomness in them, right? So I thought I need to find a big problem to shut them off, okay? Fortunately, I found one when I was in IIT Kanpur. There's this company from Lucknow called PTC Industries. It's a foundry, basically, only surgical foundry. So surgical equipments, all these they made. But it's so popular, I think it's the best in the country, and also probably come very close to best in the Asia. They get lots of order. I visited their plant, huge, very sophisticated foundry processes. They have written an Excel code. So I used to, when I was in Kanpur, Sarvana may have attended one of those or know about it, that I used to offer every year a short course, like 5-day course like this. And that I used to keep open for anybody, student, faculty, industry. I would get 80 to 100 people, sometimes maybe 50 to 80 people coming, because that time it was new, ideas were new, they wanted to know. So when one of those, that person, the R&D chief of that company also came to know and came, and he said, Professor, I need to have some time with you because we have a problem that maybe your methods can solve. So in one of the afternoons, I sat with them and they showed me an Excel code. So what the problem is that you melt some metal. This is not from their company. They have lots of restriction they put on me. After I solved it, I think it was probably early 2004 or 5, I did it. And they put on me a 10-year restriction that I cannot talk about it. Okay. So after that is over, then I did all the extended work I'm going to show you. They melt some metal, and I know exactly how much. It's 650 kilos. It's a big vessel of metal they will going to melt. And now they have to make lots of castings. And they have like 2 months, 3 months of order now. And this guy, chief, goes around, gets more orders and all that, so he's hardly there. So he says he wants to schedule it for at least a month or 2. Okay, and give the whole schedule to the foundry people, and they will just do it accordingly. So he needed a code that's going to do it. So he wrote an Excel code where all of these are fed, weight of every castings that they have to make, and then the vessel size, and then how many per day they can do this. It's about 13 times they can do per day, because it takes about 2-3 hours to melt and everything. It's more complicated. They have 2 different size of vessels, but when we gave the code, we had all these details worked into it. But here I'm showing you with 1 vessel. Okay, so all these parameters are known beforehand, and now you melt 650, you are going to pour it to fuel, and then let's say you've utilized 630 kilos. 20 kilos are still there, you could pour, but none of them is less than 20 kilos. I'm giving an example here. What you're going to do is going to be a waste, right? And then you melt some more, come back after 3 hours and pour again. Then you think, oh, what if I could have done with 640? Then maybe 10 kilos would have been a waste. So if you do it 1 or 2 times, you could do manually. But if you have to do 13 times a day for 2 months, it's a lot of order to do manually, a lot of scheduling. So you need to use an algorithm like this. So they set it up on an Excel sheet and they run it after dinner, and next day morning they will get some results. And they would get about 70 to 75% utilization. So 25 to 30% of the 650 will be wasted. They could manually fix it also, they said. So it's not something that they're proud of, but that's all they were doing. Okay. He said, if you can give me something 90% or more, we would be happy. Okay. So I took that as a challenge and I said, let me see what I could do. So I calculated how many variables do I have. If I go for 2 months of projects, 2 months of scheduling, it's about 50,000 to about 100,000 is what you get. So it's, in any standard, it's a very large problem. What's the problem? Here is the objective function where xij are your variables. It says from the ith heat, ith time you heat 650 kilo, jth casting, how many copies you're going to make, because every casting maybe you have 10 copies to be made, 8 copies to be made, like that. And this is the total metal utilization which you want to maximize. This constraint says, so let me give you an example. This is an X matrix because Xij is a matrix, right? So this is the first hit. It says from the first hit, you make 1 copy of the second one, 1 copy of the third one, 2 copy of the seventh one, 1 copy of the eighth one, and you will be utilizing 623 kilos out of 650 of melted. So the utilization is 95.85%. Next one, you do this, you have utilized 94.62%. Like that, if you do 10 times, you may have met these small orders. First one, you have to make 7 copies, second one, you have to make 7 copies, like that. And you are meeting them. So average of that is you want to maximize, this is this actually. And this constraint for one particular I is that this has to be less than equal to 650, because you cannot utilize 651 kilo because you haven't melted 651, you only melted 650. The numerical methods doesn't know that, so you have to put that as a constraint. This is the resource constraint, which says whatever you are utilizing should be less than whatever you have melted. Make sense? Then this constraint says the order sum up has to be 7, has to be the given R. It's an equality constraint. Okay, so now if you look at this, this is a linear function of x. Objective function is linear to x. This constraint, there are many, but they are linear in x. Look at that, linear in x. There is no x square. This one also linear in x. So everything is linear. What do we call it? Linear programming. And I told you with linear programming, we can go to millions of variables. So what's the problem here? We only need 50,000 to 100,000. The problem is this. Every x, which are these numbers, can it be non-integer? If this is 1.5, what does it mean? I'm going to make 1 copy of the second one with the 650 and then 50% of the another one. Is it allowed? No, either you completely do it or not do it. So 0 or an integer is allowed. This itself makes all the linear programming stuff very difficult. I showed you the only way they do it is branch and bound. And I also mentioned to you yesterday that this is an exponential method. That means if you have few hundred variables, it's probably okay. But if you go to thousands, they don't work anymore, right? That's the problem. So what we do is, as always we do, first we try a standard existing code. So we actually tried Cplex, and another method we tried with Octave, which is like parallel to, it's a free version of MATLAB called Octave. GLPK, they have one to do the integer linear program. Later on, we also tried Gurobi optimizer. So I talked about this, it's an exponential method called branch and bound. Let me show you some results. So I first took a very small version of the problem. I adjusted the weights and all that, number of copies in a way that I need about 300 variables. Small size problem, not 50,000. So when I run Cplex, let's forget the GLPK. When I run Cplex, that's 310 variable, it takes me 0.05 seconds. Okay? And no standard deviation when I run it many times, and I get 99.256%. This is the known optima. I mean, I could prove this is the optima. Only 0.05 seconds, Cplex. Excellent, right? Then I increase to 1000 variable, I increase all these data. Now it takes 0.13 seconds, which is also very small, very quickly it does with the optimum. Then I go to 2000, it cannot solve. Okay? So you see, small numbers, excellent. You can use it, but anything larger, it cannot. So then I was wondering, when does it work? When does it stop working? And I found that around 1800, it does work. It takes 1.22 seconds, but it works. 1900, doesn't work. 2000 doesn't work. So I took a 2000 variable problem and I want to understand why it doesn't work. So what I did, I took 2000 variable, we ran it with time. So this is in seconds. We ran it for half an hour. Okay? And there are two things it prints out, among other things. One, the blue is how many nodes it has opened. How many branches it has made. Because you remember, it assumes it's real. And then all the variables that are not integer, it has to branch, right? So how many such nodes it has opened? It turns out, when I am at 30-minute range, it has opened about 35 million nodes. 35 million nodes it has opened so far. Of them, this side is how many left, how many are still to be fathomed. Unless you fathom everything, you don't have a solution. I mean, you don't have the final solution. You see, they are fluctuating because sometimes they can fathom more, sometimes less, but still about 35,000, 34,000 or so, still open. So I thought, oh, we terminated a little early. Maybe we should go another half an hour, we should. So we end up running for 15 hours. Both are increasing, which means it's a problem that dimensionality is beating the algorithm. This algorithm is not able to handle the dimension, no matter how long you run it. Okay, so this is only 2,000 and we have to go to 50,000. So I thought, no, these are too structured methods. I cannot even change them. So if I have to give them a solution, I have to think fresh. Okay, so we thought of generating or creating a population-based integer linear program. It's a very simple code. We customize everything. We customize our initialization. You see, look at one of these constraints, this constraint. Sum of few numbers. Let me take an example. Let's forget the 2-dimensional. Let me say this equal to 5. One of the constraints is like that, right? If I want to create an initial population that will satisfy these constraints, how can I do? All the x's can go between 0 to, let's say, I take a maximum number. Let's say I divide this by 5. Maybe that's a good idea. I divide this by 5 and make it equal to 1. It's the same constraint, right? So then let me say that because none of them can be 5 because their sum has to be 5. Let's say each x goes between 0 to 1. Each x goes between 0 to 1. And now I'm looking for a few fractions that will add up to 1. How can I create an initial population member that will satisfy this constraint? Any idea that you may have? So I'm actually trying to have 3 numbers which are all fractions that should add up to exactly 1. How can I achieve it? This is how you have to think when you are doing customization. Any ideas come to your mind? Okay, you can think about it later, but let me give you my idea. Let's say each of them I randomly create a number. Let's say this one is y1, which is between 0 and 1. Take a number. Let's say this is 0.4. Next one I created, let's say 0.6. Next one I created, let's say 0.2. Okay, randomly between 0 and 1, 0 and 1, 0 and 1. Is there sum happens to be 1? No, because they are randomly created. But let's see, what's the sum? 1.2. Then, where did I go? Then each of these number I divide by 1.2. Okay, and I call my x1 is this, x2 is this, x3 is this. What if I add them now? What is it going to be? Always 1. Isn't this a nice trick? And I could do this because I am using a very flexible algorithm. I could do anything. I can create my initial population any way I feel like, right? So I create every initial population member satisfies all of these constraints. If you do this little trick, which doesn't take much time to think, you are already starting with a good population. Okay? Now, fixing this doesn't mean this gets satisfied. So we have a mutation operator or called repair operator, which I applied on top of this to try to fix this. So that's my initialization. So it's not a totally random population. It's satisfying at least some part of the constraints. And then mutation to it I'm going to describe to fix the inequality if possible. Then we assign a fitness, and there is a way, I'm not going into the detail, but there is a problem specific way you can fix R here.